तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome everybody to the lecture on computer graphics. We have been discussing in the last two classes the concepts of solid modeling, and related to that we had discussed various concepts. The most noticeable among them was the boundary representations, and also we had discussed the concept of sweep representations. If you remember carefully, prior to these two, I did give you an idea of the concept of regularized Boolean set expressions, and which involves Boolean set operators like union, intersections and difference, and we had seen using those how we could create complex objects from very simple primitives ones. We will see extensively today the use of Boolean set operations and how to create complex objects from that which is based on the principle of union, intersection and difference operators, and we will see the area called constructive solid geometry, which is a very important part in solid modeling. But we will just go to the last few minutes of where we left off in terms of boundary representations, or B-reps as it is called. B-reps are boundary representations where a solid is considered to be a polyhedron bounded by several polygonal planes, and each of these planes will have a set of vertices, will have a set of edges, and so we need to maintain a vertex table or a vertex list, also an edge list and a polygon surface table. So, we will start from where we left off in the last class, where if you see in the slide a simple example of just two surfaces out of a solid which are adjacent to one another. One is a triangle, and of course, the other is a quadrilateral, and they share an edge E3, and the vertex table stores the coordinates of the 5 vertices which are involved in building up these pair of surfaces or polygons, and we also maintain an edge table which maintains a list of edges involved in these two surfaces, and the edge table entries contain the pair of vertices which are joined to form the edge. We also maintain a polygon surface table which contains the list of surfaces which are enclosing the polygon. Since in this case we have just picked up two adjacent surfaces, the list contains the labels of the two surfaces S1 and S2. The first surface S1 will have the corresponding edges E1, E2 and E3. If you look back, this is what S1 contains E1, E2 and E3, and the second surface S2 contains 4 edges E3, E4, E5 and E6, E3, E4, E5 and E6. Now, these three tables, the vertex table, edge table and the polygon surface table, does not give you an idea of which edge is shared between these two surfaces S1, S2, because there are solid body constraints about number of edges to meet to form a vertex and number of surfaces which could share an edge. So, based on that, we built up a complete expanded edge table which will contain, is basically the same edge table with the surface information now appended or attached to that list of entries, and we can see that for each edge there is one or two surfaces. The edge E3 is shared between two surfaces S1, S2, and it runs from vertex V3 to V1. So, that has been entered in the entry for E3 labeled, and for others we also store the pair of vertices and the corresponding surfaces. So, that concludes the discussion of boundary representations. And where do you use these boundary representations? In fact, the bigger question is why do you have to represent solid objects? You have to represent solid objects because you have to give a visualization of them in a computer screen in computer graphics literature. So, you have to provide a wireframe diagram, then provide shading, and when we go on to concepts of shading, before that of course, we have to discuss concepts later on about visible surface detection, backface culling. We will see the most important attribute which will be necessary for a polygon when we process them, either in terms of ordering those surfaces based on the coloring you need to do. We will see that the polygon surface normal is an essential parameter or an important property of the surface which we need to compute. So, let us look at equations of a normal n of an arbitrary polygon, assuming the polygon has n different vertices or n edges. Remember, any polygon, we talked about polygon filling, and if you remember that, you will definitely remember that the number of vertices is equal to the number of edges. That is a small n in this sigma operation, the summation operation, and there are 3 parameters a, b and c which are listed here. If you carefully see, the index is running from I is equal to 1 to n, and it is a summation of terms which involve a pair of a product of 2 terms. Each product again is subtraction of 2 coordinates. So, the coefficient A involves the coordinates y and j, the coefficient B involves the coordinates z and x of the polygon vertices, and the parameter C involves the coordinates x and y. What are these xi, yi and zi? They are nothing but the coordinates of the vertices of the polygon, n of them, okay? And the summation goes from I to 1, I is equal to 1 to n. So, the first to the last one, and you can see generally that j is equal to I plus 1. That means, you are subtracting the immediate next successive vertex from the previous one, or and of course, the only one condition which you need to keep in mind is that when I is equal to n, then j is equal to 1. So, okay. So, these 3 equations which we have just seen now for the parameters a and b and c, they in fact are the direction cosines of the surface normal n of a polygon. So, that means, if you remember this equation, and for a polygon with 3 or more vertices, if the vertex coordinates, that means the xi, yi and zi as in the vertex table are given to you for a particular polygon, then you should be able to compute the surface normal n from these set of coordinates. We will talk about the surface normal n more when we go to concepts later on for the various lectures on shading, concepts of visible surface detection, backface culling and all that, but for the moment now, please remember these equations of to compute the direction cosines of the surface normal n. Now, just a little bit, put a little bit more into those equations. Now, we see that cyclically you keep on rotating clockwise and anti-clockwise and keep computing the products of y, z and x coordinates, then multiply and sum it up to get a, b, c, and let us assume a very simple case of a triangle. That means, you are talking of a polygon with 3 vertices. Okay. So, that means, I will be running from 1 to 3, n is equal to 3, the small n which you see here in ABC, and if you break open one of these, let us say you take the last expression c is equal to the summation of x and y terms, the coordinates of the vertices, then you can break open this expression and write like this, which you can again simplify as the one given on the bottom of your screen. So, that is the simplest way by which you can write the parameter c, and in fact, you can do that and also write the same thing for, similarly you can write for parameters a and b. Let us go back and see what we did was, I repeat again, we just take n is equal to 3 and you write the 3 terms for the coefficient c like 1, 2 and 3 terms, and then open up the factors, and you can get a few terms cancelled out, and you will be able to simplify the expression in this form. Please check it out yourself right now as we are reading these expressions here. Please work it out right now. So, that is what you get for C, and similarly, if you are able to obtain C, you should be able to extrapolate the logic and write expressions for A and B. Either do that or use the expressions of A and B given in the previous slide and open the sigma term and write these expressions. Okay. So, that is how you get A, B and C. These expressions can also be written in matrix form. Okay. If you see carefully, of course, the expression A, B is given on the top of your screen, the expression of C was given earlier, and if you see for yourself that the determinant of this basically becomes the determinant of x and y for C, x and z for B, and y and z coordinates for the coefficients, for the coefficient A, parameter A. So, this A, B, C, which are the parameters are the of the surface normal, the direction cosines of the surface normal, n can also be written very simply in the form of an expression using determinant of a matrix 3 cross 3 symmetrical one, excuse me, 3 cross 3 matrix as given here. If you keep a watch on this A, B, C and move forward a little bit, you will be able to find that these are nothing but the solutions of the set of equations given by this particular expression. Okay. I leave it as an exercise for you to try out that if you are given an expression like this, a linear equation where A, B, C and D are the parameters to be computed, and there are 3 of these the x k, y k, z k, nothing but the coordinates of the vertices, then for k is equal to 1, 2, 3, you can write these 3 expressions for from this top equation here, and you will be able to compute A by D, B by D and C by D as the one which is given here in the bottom. So, what will come out is the D with the denominator of the coefficient will come as an expression like this, and of course, the numerator A, B and C will come in the way which is given here. So, what is this D? Remember this when you write the set of 3 equations based on the vertices of a polygon, you are basically trying to compute the surface normal n, and that is what you get as a solution, because any 3 points form a plane, and that should be sufficient for you to define the plane uniquely and obtain the surface normal. The significance of this denominator term D is very interesting. In fact, the D we will see soon that the factor D will be basically 0 if the coefficient, if the plane passes through the origin. If the plane passes through the origin, the factor D is equal to 0, otherwise the D is equal to a dot product of n dot p, where p is any point on the polygon or the plane, and n is the surface normal. So, it is a dot product in the negative sense between the vector joining any point on the plane P with the surface normal. In other words, what is D? You can almost visualize that this is going to be the distance of the plane, perpendicular distance or shortest distance of the plane from the origin of the coordinate system. Okay. So, that is what is given by the factor D. Again, I repeat again, the plane passes the origin, the value of D will be 0, and hence that is the case when the plane will be forced to pass to the origin when the value of D is null. Okay. So, this is how you compute the, remember these expressions can be used to compute the surface normal. So, that brings us to the end of the discussion of boundary representation. We will actually start to discuss a new concept of octrees. So, let us before discussing the concept of octrees representation of solid objects, let us try to visualize a 2D quartree representation of an image or a view. Okay. So, what is done in this particular case is the entire image is split into 4 quadrants. Okay. That is what will result in the quartree representation. So, you have a 0, 1, 2, 3, you can label it clockwise or anticlockwise as you may feel like, and then depending upon the region of interest, we can divide one of these quadrants into 4 equal parts again and keep doing it and so on. So, this is a typical representation which is used in concepts of image processing and is called an image pyramid representation as well. The concepts are closer to this, but right now if you look at quartree representation, what we mean is the following, that the image consists of 4 different parts, and these 4 different parts are 4 children of a tree structure which can be used to represent this image. And since each node can have at the maximum 4 children, okay, or 4 subnodes as it is called, as you may call it, then hence the name quartree. So, if you look at this representation, and I am interested to just locate a small subregion which an image which is somewhere here, we will say that this subregion is in the second child of the root node which represents the whole image, and then under the second quadrant it is under the 0th subnode or child, and within that again under the third. So, if you look at the quartree representation of this particular region, here is what you will get. The root node, which is of course on the top, you have to assume that that is what the image has 4 children, basically the root has 4, and each of those could again have at the maximum 4 different subnodes or children from left to right order from 0 to 3, but since you may not split all the 4 different sub quadrants or quadrants. In fact, only the second quadrant is split into 4 parts. So, you can see here that the root node, which is the child at the top layer, is split into 4 different parts. So, 0, 1, 2 and 3. So, you can of course draw a root node at the top which represents the image, and that will have 4 children in the top layer or the first level of the decomposition of the image structure, and the second one is again split into 4 parts. As you can see here, this is the second quadrant which split is again into 4 parts, and the information is in the 0th sub quadrant of the second quadrant. So, if that is so, you can see that is why the 0 is split into 4 parts again. Okay. You can I hope you have a visualization of what we had seen in the previous slide, or you please draw this yourself on a sheet of paper and try to analyze this and try to visualize this decomposition with respect to the quadrant representation. Quartree representation is given here with respect to the image split done in this particular slide. So, if you go back and forth now in the lower level of second level of decomposition, the third Quartree, this I am sorry, the third quadrant at the second level of decomposition is further split into 4 different parts, and you have the first one which is full, which is of area of interest. It basically means that if you are interested in this particular area, or it could be even at the lowest level a pixel, because if you keep on decomposing like that into several levels split into 4 parts, each of them split into again into 4 parts and so on, if you keep doing that at very different levels of decomposition, at the very lowest level of the tree, you will have if you are going for maximal decomposition that is possible, at the very lowest level you have a set of pixels for each particular child. The leaf nodes will be a pixel if you keep on decomposition to the maximum level extent and maximum extent which is possible. So, you know that this could be a pixel or a small subregion as given in the slide, and it is under in the first level under quadrant 2, then under that quadrant 0, then under quadrant 3. So, 2, 0, 3, as you can see here, 2 is decomposed into 4 parts, then the 0 is decomposed into 4 parts, and the third one is again decomposed into 4 parts, and this particular region which is labeled as 1 and is labeled also in this picture with a certain color indicates that that is my area of interest, and that is where my information is, or that could be the lowest level of pixel if the image has only about say about 16 cross 16 image or something like that. So, for an image with n cross n pixels, you can see the maximum number of levels which you can have in a Quartree is a log of n of course to the base 2. That is what you need to have. That means, if you simply have a 2 cross 2 image, you can decompose and make just one level of Quartree. If you have a 4 cross 4, you can decompose into 2 levels. If you have a 8 cross 8 image, you can decompose into 3 levels. If you have a 16 cross 16 image, you can decompose in 4 levels, 32 5 levels and so on. So, that is the figure which you must keep in mind, and that is what you do for an image in terms of Quartree representation, and that is in 2D. Remember, it is not a solid, image is not a solid. Here we are talking of solid modeling, but what we will do now is, if you have understood the concept of Quartrees representing images in 2D, we can visualize that we can extend this philosophy or concept to 3D, where we can represent objects with the help of Octrees. If you look at this figure, that I have taken a very large cube, and split it into several parts by planes. As you took a line to split a plane, an image plane or any 2 dimensional space into 2 parts, okay, took another line and split into 2 further parts to create 4. What we are doing here in this case is to take a plane and split this volume into 2 equal parts. Let us say, if you consider this particular classroom in which we are sitting and listening to this lecture, I can take a plane between you and me and split this classroom into 2 sub volumes, okay, as we had done in the case of a 2-dimensional image space, where we took a line and you took an horizontal line or a vertical line, does not matter. If you are taking a line and splitting, you you are splitting the two dimensional space into two equal subplanes or subregions. Here in the case of a three dimensional case, the line becomes a plane. So, I take a plane and split this classroom into two different parts or sub volumes or subspaces in 3D, and I can take the plane either as a vertical one or a horizontal one, and again vertical could be aligned between you and me, or it could be orthogonal between my line of sight between you and me. So, there are three possible planes along the three orthogonal planes, coordinate planes, or it could be, you can visualize them to be normal to the three orthogonal axis of the xyz coordinate system. So, if you do that and do the same operation on cubes, you can almost visualize, you can see I have taken a vertical plane which is here, let us say, and then you take a horizontal plane which lies flat and another vertical plane which is orthogonal to both. So, if I can take three planes and divide this classroom, any volume for that matter, any cube, any rectangular parallelepiped, any subspace, any volume in 3D can be split into 8 different parts by taking one plane here, one plane there, and another plane like that. 3 orthogonal planes is what you need to take, okay? And if you do that, then you are splitting this volume, let us say what we consider as a very large cube, into 8 parts, okay? 8 equal, of course, it is a cube, then we can, and if you take symmetrically located planes, then you are dividing the space into 8 equal sub volumes or parts or regions in 3 dimensional spaces. And hence, now in the case of an image which we represented by quadtrees, after using 2 lines and splitting into 4 sub regions, we say here that the volume or the 3D space is split into 8 equal parts by 3 different planes. So, now the root node which represents the volume of the cube will have 8 children. Okay? And in the case of a quadtrees we had 4 children, and now in the case of the octrees we have 8 children. So, that is what is given here, and look at the levels which have been done clockwise. The plane with the volumes to the right of the vertical plane, if you consider the vertical plane, as you have a 0, 1, 2, 3 and a 4, 5, 6, 7. So, it is something like that you have 4 smaller cubical volumes on the right hand side, 4 equivalently smaller cubes on the left hand side. So, totally you have 8 sub volumes or volume elements, and hence this term called voxels are often used to represent elements of 3D volumes. As in the case of an image, you already know the term pixel, which represents the word picture element, is the meaning of the term pixel. You have in 3D equivalent to pixel the term called as voxel. So, Octree is nothing but a voxel based representation. We will see it is basically called a spatial occupancy, is equivalent to a 2D region occupancy. Here we will talk about spatial occupancy, but right now let us understand the meaning of the word voxel, which calls of a volume elements, and that means in the first level of decomposition you are coming with 8 subregions which can be also visualized as very large voxels. It could be that each of those sub volumes could be a unit element which you are using to represent the 3 dimensional space if you are not decomposing further. But if you are decomposing further, like in the case of an image where we took each of those quadrants and split into 4 equal parts, we can do that similar thing in the case of a quadtree representation, where what do? You basically take each of these any one of these or all of these 8 sub volumes and use 3 planes again to split it into 8 equal parts again. So, voxels depends upon what level of decomposition you are looking at. The smallest element which you will get is called the volume element or voxels, and let us try to look. This is the first level of decomposition, where the root node will have 8 children labeled from 0 to 7 in ascending of course in levels, but you can level them in any order depending upon what sort of sequencing you want for the representation. You can order those on the positive x axis and then on the positive y axis and so on, and these are the 8 different children. So, I hope you are able to visualize this 3 dimensional figure where there are 8 sub volumes or 8 sub cubes created out of this larger cube by 3 different planes, which will partition this space into 8 voxels if you are not decomposing further. So, that is the first level of decomposition, but you can split further into 8 Other parts, this is done in this case where the voxel 0 after the first level of decomposition, the voxel number 0 is split again into 8 equal parts, and again those 3 similar planes are used. As you can see here, there are 2 vertical and 1 horizontal plane, each of them are orthogonal to one another, and you can see within the voxel number 0, if you compare this figure with the previous figure, this is the unit volume. The 0th voxel unit at the first level of decomposition of the 0th unit volume, let us say, is split into 8 parts, and you still have 0, 1, 2, 3 on the right hand side of the at the second level of decomposition, and similarly 4, 5, 6 and 7. 6 is of course hidden, but you can still label that if you want, and that is what on the right hand side. Why did I label with a color the volume element 0 at the first level of decomposition and then the number 4? Well, we will say here that our interest is in this unit 4, or this in the Octree representation, the node 4 at the second level of decomposition is of our interest because the object lies there, let us say. Let us say the object lies there, or the object is a cube which just occupies exactly the volume occupied by the 4th node at the second level of decomposition. And since the 4th node is at the second level of decomposition falls under the 0th node of the first level of decomposition here. So, that is why you have an arrow running from 0 to this subdivision, and then the 4 is labeled. In fact, if you have the occupancy or the object occupying some other position as well, which falls under the different nodes at the first level of decomposition itself, you may need to break and subdivide the other unit volumes at even the first level of decomposition. But let us say for the time being that our object only occupies the unit volume 4 corresponding to the node 4 at the second level of decomposition. Hence, at the second level of the tree, the 4th will be labeled. Of course, if you feel that there is some information also, let us say in some information in terms of parts of the solid present in the third node, let us say the third node here at the second level of decomposition, you may need to split it that further. Okay, so that those arrows, the pointers only will exist for those parts where solid bodies exist. So, what you are talking in a 3-dimensional space is that you are leveling those nodes only which is occupied by solids. Okay, and those nodes which are pointing to null, let us say, or are empty, will not have any solid object. It is a vacuum or a space which we are not interested in. So, this is the way by which octrees are used to represent solid objects. Okay, and this is how you do that in terms of the representation. Now, let us say in this particular room, you are interested to know where a particular object is lying. Okay, in terms of its quadric representation. Well, let us say it occupies some space for which you know exactly, let us say the x, y, z coordinates of a set of polygons which is occupying a small space. What you need to do for an octreed representation is, if you are interested in this full room which is our region of interest, you first split at the first level into 8 equal sub volumes. Then you find out within these 8 which of the sub volumes is this polygon or the solid lying. So, take that one out of those 8 and then again split into 2 parts. Now, if that solid is occupying a part of 2 different sub volumes or even 3, you need to split all of them into 8 equal parts. So, you keep on doing till you come to the lowest level of decomposition, where you cannot go down below in terms of resolution of defining the minimum unit volume, which is in fact called the voxel. So, you have to visualize this octree scenario as if that this entire classroom or the room which you are sitting now, let us say, and watching this show, is built up of small unit cubes, and those unit cubes are vacant or free if there is no solid object occupying that portion. Okay. If there is a solid object occupying that portion, then the corresponding node or leaf corresponding to, which represent the sub volume at certain level of decomposition has to be set to on or has to be set to 1. or it will not be a null pointer, it will not be empty. So, that is the concept of representations of solids. As you look here, if we say into the slide, I repeat again with a simple example of only about 2 levels of decomposition at the most, is that if a solid occupies a part of 4 or even the full part of this sub volume 4 at the second level of decomposition, we will say that unit will be labeled and it will be set to 1. All other units in the first level of decomposition and the 7 of them at the second level of decomposition, if there are no solids occupying that particular space, we will set it to null. Okay. And of course, why did we break the 0th unit sub volume at the first level of decomposition into 8 equal parts? Well, if you go back to this slide, and if this entire 0th sub volume was occupied by one particular cube, then I would not have broken it. I would say that would have been set to 1 and the rest would have been 0. But since a part of that 0th unit volume at the first level of decomposition is occupied partly, I need to break it. So, I break it up into 8 equal parts and look which of those 8 are again occupied. Okay. In this case, of course, I have shown that a cube occupies that 4th node, or the volume occupied by the represented by the 4th node, and hence that is the one which is set to 1, all others are kept back in. Now, it may be possible that a part of that 4th node is occupied, not the full one. So, in that case, you might have to again break the 4th node into 8 equal sub volumes, similarly with 3 planes, or if you feel that there is some occupancy by solid objects, by planes or whatever it is in the 3rd sub volume at the second level of decomposition, you need to break it further and so on. So, this is the explanation which shows how to build up octrees and for representing a solid. Okay. The minimum unit volume you have to specify, beyond which you cannot break out. It is equivalent to visualizing a pixel in image, you cannot break a pixel further, that is the lowest level in a quadtree. Similarly, in the case of an octree representation, you can have a voxel which is a minimum unit volume. You will say, I will not go below 1 inch cube, let us say some minimum volume, or it could be 1 centimeter cube, 1 cc, cube of 1 centimeter length, breadth and height, or even 1 millimeter cube, let us say. So, you define your volume with respect to the world dimension and try to fit objects present in a particular environment, could be a classroom or even a simple scenario where you have just solids, rigid structures like cubes, cylinders, spheres and all that present in a particular room or a space which is your interest. So, this is how you build up octrees. Okay. So, we will move on to the next representation, which is in fact the last one which I will be covering. There are of course a couple of others which I will just name them, and of course I have named them also in couple of classes back, but this is a concept of constructive solid geometry, which says that you can combine more than one object. You can combine more than one object and build complex structures. In this case, let us say you can look into these 2 different structures, one is a cube, another is a pyramid with a rectangular base, and you need to join these 2 objects and these 2 solids. Well, if you remember, in a couple of classes back, we did talk about Boolean set expressions, okay? And the 3 operators in the Boolean set expressions were union, intersection and difference. You remember them? Union, intersection and difference. And we also seen conditions where we need to probably eliminate a few hanging points, lines and surfaces which result due to these Boolean set operators. Okay? And that is a process called regularization, where we throw out hanging points, lines and surfaces even, because those are not solid, they cannot just exist on its own in a particular space. You have to have a solid, okay? And that is what we are interested in, to model solids, not model points, lines and surfaces. Okay? A thin sheet of paper should be also bounded by 2 surfaces, one on the front and one on the back side. Okay? And so regularized Boolean set operations or expressions are used in constructive solid geometry to build up complex structures from primitives. Of course, there is another concept of area called the primitive instancing, which is used for CAD tools. You can have primitives at the very high level, such as which could be for an assembly plant, it could be a gear assembly, or it could be a spanner, or it could be hammer or whatever it is. So, you can have different type of assembly structures as primitives. You instantiate them with the help of CAD tools and then combine them and fit them. That is all possible, but you are talking of graphics object modeling here at the very low levels. We assume the 4 simple primitives, let us say, which I kept on giving examples in the last 2 classes, and even today I am using a cube or a rectangular parallelepiped, a sphere is a one, a cone, cylinder, and maybe the 5th one could be a pyramid. So, assume that these 4 or 5 primitives are available to you, because you can generate all of these by boundary representations or sweep. It is very easy to generate all of these in terms of boundary representations, generate the XYZ coordinates with the help of what we call as sweep representations. Of course, with sweeps we can generate curved object shapes as well, but let us start with these primitive solids. We can visualize the simple 3D geometrical shapes very easily and try to build more complex structures. So, we will see 1 or 2 building blocks which are used to compute and generate more complex structures out of the low level primitives. So, if you look back into the slide, you have a pyramid with a rectangular base and you have a cube, and I want to put this cube on the pyramid on top of this cube. So, this is the operation which I want. I desire to make a structure which should look like this, and I will say that finally this is my structure, this is my goal, which will consist of 2 parts, a union of a cube with a rectangular with a pyramid with a rectangular base, and in such a manner that the dimensions of the base of the rectangular pyramid is equivalent to one of the faces on the cube on which it is sitting. So, this is a simple union operation. This is a simple union operation. Of course, you can do other operations such as difference and intersection, but if you look at union operations, of course, assuming that you know how to regularize it by throwing off hanging points, lines and surfaces, you have to visualize here that I am trying to generate solids which may be interpenetrating or may not be. Typically, if you say that there are 2 solids which I am trying to unite, in reality of course, one solid cannot enter another solid. So, if you want to put those constraints, you have to put that saying that I need to position them very correctly such that my faces do not interpenetrate. That is, one surface of one polygon of an object A should not enter another polygon of an object B. That is true in the case of solids. You can put a solid inside one, but you cannot collapse them in such a manner that one face of one object enters another one. Okay, so that is what. But of course, you depends upon what sort of object hierarchy and what sort of object modeling you want to do. If you really need to have complex structures, sometimes you can have one object, a few polygon faces of an object really interpenetrating or getting inside the plane of the other one, because we know how to clip polygons with respect to another in 2D and as well as in 3D. So, assume you know that that is what you could use, but in this example what we are saying is we want to create this structure where you must position in such a manner that the planes do not interpenetrate and just touch each other. So, you create a union, and when you create that union, of course, the middle surface is what you need to throw out. I leave it as an exercise for you to check the Euler's equations with the vertices, edges and faces for this particular structure. So, constructive solid geometry, continuing on that, if you have a look here, this is what I want to generate. Say, let us say if I want to generate this particular structure, what does this particular structure say? Well, I am seeing a cylinder, a black one in front, and I am seeing a thin rectangular plate with a small height, and they are not only adjacent to one another. It is, in fact, we have to visualize that the plane is coming out of the cylinder. Okay. Of course, the cylinder can sit on the plane, it depends upon where you want to position them, but you should be able to generate a scenario where the plane and the cylinder are mixed at the base. That means one object is entering into another. So, I will say this object is a union of these 2 parts. So, I will take a cylinder which I have shaded with black for you to give a visualization for the sake of visualization, otherwise the colors have no significance, and I will like to say that the structure at the root node in constructive solid geometry in this particular example is a union of 2 different structures, a cylinder and a wedge type of a structure, a rectangular parallelepiped, a very thin one where the left bottom part is truncated or broken, is as you can see for it. So, we would like to position the cylinder at one point and take the union of these 2 structures. but cylinder is easy to visualize. You can do a boundary representation of cylinders very easily using sweep. How to generate this particular structure for the rectangular parallelepiped? Well, I will say that this is also based on the combination of two different objects. I can say that I can take a rectangular parallelepiped and then subtract a small portion of that with another small object. So, if you see the large object on the left hand side and I take the, say that is object A, and the right hand side have object B, then the object here, which is this broken rectangular piece of rectangular parallelepiped with a broken part, can be obtained by taking the operation A minus B. If A is the left hand object here, which is the larger rectangular parallelepiped, and the B the smaller one, and then I can have A minus B. Of course, you need to position the B suitably such that you know which part to be taken out or truncated. Okay, so, this is how an example how constructive solid geometry could be used to generate complex structures. Of course, there is no end to create more and more complex structures. If you visualize that you need to add some more objects to this, please go ahead, because this is not the final object, this is only an example. You can bring in other objects, maybe a sphere, maybe a cone or something else, and then unite, subtract or intersect or take a difference of some of the two objects and add to this and create more and more complex structures. But the most important part of this is to visualize of what you want to create. What you want to create, if you have a visualization and you can model them in mind, saying that this is probably union of two or a difference of two or intersection of two different solids which are again complex in some sense, then you can break it into subparts and so on and construct this tree, where at the lowest level of the tree you will have the primitives, the geometrical three dimensional simple primitives which I talked about. Again I repeat, cube, cone, cylinder, sphere, and maybe a pyramid with a rectangular, or even you can visualize a hexagonal base or an octagonal base. So, you can take 4 or 5 of these 3D geometrical primitives and then start to do the Boolean set operations. Of course, you need to use regularization to throw off these hanging points and lines, but you give these operations, create more complex structures and go up higher up the ladder. So, that is what you do. In this case, we are just talking about just two different operations, a difference here and then a union here which could create this particular structure. So, let us take another example of CSG operation using regularized Boolean set expressions. Say, let us say I take these two structures. Now, I am not giving you the final shape, and we are giving example again of a cube and a cylinder, and let us say I position them in such a manner. Remember, virtual reality, all the solid objects, I keep repeating again, one object does not enter the other one, but in this case the cube has entered the part of the cube is inside the cylinder, and I want to take the do an operation which will result in this particular structure. Can you guess what this operation will be between the cube and the cylinder to get this? Yes, it should be an intersection operation. So, we have seen union and difference earlier, and this is a nice example of an intersection operation. That means, intersection of the two solids, the cylinder and the cube, will result in this particular structure, and this is the common volume between these two. The intersection is the common volume. You want, what do you want to do? This is not our main aim. Our aim is to probably create this structure, which is a part of that rectangular parallelepiped chopped off, in such a manner that you basically as if this part is missing from that structure. So, what do you do? Take a cube again or rectangular parallelepiped and position this wedge at a corner where you want to get this volume subtracted away, taken away. So, what you need to do is take this cube, put that, and then use a differencing operation. So, it is this entire cube minus this resultant structure which will produce this final structure. So, you can see that again it is a two level of decomposition or construction of the CSG. At the lower level you will have intersection operation and then a difference operation which will create that final structure. And of course, at the lower level of the as the leaves of this of the tree for the CSG, you will have the cylinder, you will have two different cubes, okay, or one cube, one rectangular parallelepiped, and the difference the intersection operation creates the structure in the middle, and that is again used by the last operation to create the final structure at the root. Okay, so, this is a typical example of a constructive solid geometry tree where the object is on the top and which is due to the resultant of two different operations, let us say, which will unite finally and create this CSG object. and we will say that of course, CSG could be at the root, which will be a resultant of a union of two different objects, which will be again resultant in this. That means, at the lowest level I use object 4 and object 5. If you look at the right hand side subtree, the lowest level of at the leaves object 4 and object 5, you use an operator 3 labeled here to create a structure, which is again combined with the object 3 at the operator 2 level to create one object. Then you take object 1 and object 2. We of course assume here that object 1, object 2, object 3, object 4 and object 5 are 5 different, or some of them similar type of simple 3-dimensional geometrical primitives, which are used to create complex structures. So, at the final level you have two operators, uniting the left one side creating from object 1 and 2, and the right hand one creating from object 3, 4 and 5, which is again united or with some operator to create a constructive solid geometry final object. So, this is just again 2 or 3 levels of decomposition, but again as you can see that the CSG object resultant due to this itself could be a primitive now. Itself could be a primitive. So, you can talk of an object oriented hierarchism in the whole hierarchy in the whole system, where I just look at the node and say that is my complex structure, and all other corresponding primitives at the root node, at the leaf nodes in the subtree will have to follow the corresponding operations as given by the tree. So, if I give a transformation to the entire structure at the top at the root node, all my corresponding it will affect the children at the lowest level itself, okay, where the primitive objects are defined. They will also go through the similar transformation, because that is what we studied in transformations of solids in rigid structures. Okay. So, you can keep on building up a very complex structure and say you just have a pointer to your root node, which will give you the polygons representing this particular object, and what happens is that object structure is built with the help of polygons with different children at the leaf nodes, which are simple primitives. Okay, simple primitives build slightly complex primitives to simple object structures, let us say, and then again simple object structures to more complex and complex object structures. You can now visualize when you talk of complex structures, well, we are talking of designing of buildings, aircrafts, automobiles, bridges, and many shopping malls, let us say, inside scenario of a restaurant or a hotel. You want to give a visualization a certain operation. So, that is constructive solid geometry for you, a typical example of a structure. Well, if you this is another simple example of limits of surfaces along the viewing direction after a CSG operation. Let us say I have two objects, a sphere and a cube, and I am viewing it through an XY plane. If you remember the raster image display, and the viewing direction is along the Z direction. We will come back to this again when we discuss ray tracing, where you can now visualize that I pass a ray out of one pixel in the XY plane. The second diagram shows that I am viewing along on the I have taken the projection of the left hand side example on the XZ plane or YZ plane, and I am shooting a ray out along the direction of the view, which is minus Z direction, from a certain pixel xy towards the objects, and let us say that ray intersects the sphere at 2 points A and B, and it intersects also the solid cube at 2 points C and D. Okay. So, as I said before, the part of the sphere was inside the cube or vice versa, and when we result in a complex structure out of these two primitives and create a complex structure either by union, intersection or difference, this is what will result. That means, this table tells you what are the surface limits after the Boolean regularized Boolean set operations on these two objects, and where does the ray intersect that final structure. If you look at union of these two structures, the sphere and the cube, the ray will intersect at the two limiting bounds A and D. If you look at intersection, it is the common bound or the common volume between the sphere and the cube, then it will intersect in B and C. If you take a difference, depending upon whether you are subtracting the sphere from the cube or vice versa, you can have two different type of solids which will result, and you will either get the limiting B and D, or you could get A and C. So, I hope this gives an idea of what the constructive solid geometry operations could give you, using again a simple example of only two structures, and then you can keep on having more and more complex structures by adding more and more primitives. So, this is an example of the limits of the surfaces along the view direction after certain CSG operations, with examples of two solids. On the left hand side, the 3D diagram is given, where you have the raster frame buffer set of xy pixels, and the view direction is along the -z direction. You have two objects, not only the sphere is occluding the cube, but we have arranged the two objects solids in such a manner that the part of the sphere is inside the cube. Okay. So, you have to have a union operation to get the resultant structure, which could be a non-regular object in terms of not having simple geometrical features like sphere, cone, cylinder, or even a pyramid, let us say. Okay. So, the last few points before we wind up the lecture on solid modeling, because for the just to wind up before we move on to different criteria to evaluate solid modeling techniques, we have discussed about CSG using regular Boolean set expressions. And we also discussed boundary representation, and we discussed in details sweep representations and octrees. I must admit here that this is not exhaustive, but these are probably the most common one. Out of them, we will soon find that the regularized Boolean set of expressions with CSG and boundary representations are the most commonly used ones. Okay. Sweep representations are also used, but there are limitations of those, and octrees are very good to visualize, but very complex to handle and represent. In addition to this, I would request you to read concepts about primitive instancing and use of fractal dimensions to define certain other solid objects. Due to limitations of times and coverage requirement for other concepts in the computer graphics course, I am not being able to cover all the different aspects, but I have definitely covered the most 4 different aspects which are used for solid modeling. But there are other operations, typically among them are the primitive instancing and fractal dimensions for representing solid objects. We will talk about use of surfaces, curves and surfaces later on, which are also used for representing solids when polygonal modeling is a bad approximation. So, coming to the criteria in the last few minutes for comparing different solid modeling techniques, the first one is the accuracy. Okay. And we read here that octrees and polygonal boundary representations produce always an approximation of the objects. Octrees definitely will be produce an approximation, because if you look at an octree type of a structure, please go to the book by Foley Vandam, which gives good examples of those. You will find that at the surface you will find edges of cubes. Okay. It will be a set of an accumulation of cubes put together to form as if a solid. So, any surface boundaries will have edges or corrugated stepwise bounding surfaces, and those edges, vertices, and will appear very highly corrugated in the case of octrees if the surface is not smooth. The bonding surface is curved, typically you will have lots of corrugated, but of course, however level of approximation you do by going to reducing the size of your finite volume, the voxel unit for the octree, always you will have a corrugated surface. So, octrees and polygonal boundary representations, since they work with polygonal spaces or planes, are approximation of objects. CSG, that is constructive solid geometry with non-polyhedral primitives, if you can afford to do that, along with boundary representations which allow also for curved surfaces, are good for high quality graphics. This is what I was telling you. You need to represent curved surfaces, which we will talk about later on, not now, because we need to introduce curves and then talk of surfaces. But constructive solid geometry along with BREPs, which allow non-polyhedral primitives and curved surfaces, if you can put all of them together, then you are talking of high quality graphics to represent solids. Highly regular objects can be represented. The domain, sweeps have limited domain, because you can cover very beautifully the different solids for which you can generate a model for a sweep. Octrees and boundary representations provide definitely a large class of objects than sweeps. Well, in terms of uniqueness of the representations, Octree guarantee the uniqueness of a representation, all right, because in terms of if you look at other types of representations, then the problem which you will get is that it depends upon the approximation which you are taking of the polygonal vertices. You can always split a quadrilateral into triangles, or you can split triangles into different smaller triangles and all that. So, the number of edges and vertices which will be used in boundary representations finally in your BREPs for representing a solid might change depending upon what level of splitting you are going to do. Of course, the same is true for octrees, but typically the level of decomposition at the initial part, when you are looking at sub volumes in different subspaces, 1 out of 8 of those do not change much when you do not change the object structure. Of course, if you have changed the object structure in terms of scale, zoom or translate it, the Octree representation must also change, but as long as you are not doing a transformation and you are sticking to of course some degree of resolution in defining your minimum voxel unit, then what will happen is the Octree definitely gives you a unique representation, that is no doubt about it. Okay. That is not the case. So, you see that the Octrees guarantee uniqueness of representation, which may not be there for polygonal boundary representations or constructive solid geometry, because you may use different, you might approximate curved surfaces with the help of polygons, or you might use curved surfaces. So, the uniqueness is not guaranteed there. The validity, that is, the boundary represents are the most difficult to validate. That means, you must find a way to ensure that the vertex, edge and the face data structures are valid, and the face and edges may intersect in the case of boundary representations. BSP trees and constructive solid geometry are better. Well, we did not discuss the concept of binary space partition trees to represent solids. They are basically very good to represent object structures used for visible surface detection. When we talk about that next, we will see BSP is a very nice way, a good data structure to represent objects, but we will see we are talking of validity, that means trying to find out if an object structure is valid. We have looked at various constraints of the generalized Euler's equations with holes, number of vertices, edges, faces and holes, count them, count the number of holes which pass through the solid, put them in the equation and make them valid. We also try to find out how many surfaces share an edge, how many edges meet to form a vertex, and also we need to find out whether those are all fine for a solid polyhedral type of an object, but if we have a surface getting into another surface, then you may have certain need to bring in some additional constraints to find that whether there are some extra surfaces which are just penetrating into the, and that is the validity which you need to care about. So, I read again, boundary reps are the most difficult to validate. One must find a way to ensure that the vertex, edge and face data structures are valid, which you are using to represent. That means, in the vertex table, edge table and surface table, you need to traverse to that to ensure validity. And then of course, the closure after the Boolean operations, the primitive instancing and sweeps are words under that category of the closure, and the boundary representations can be used for if, but additional checking may be necessary. The last one is the efficiency, which we will wind up. Octrees are better for hardware based solid modeling for a faster response with coarser pictures, but most algorithms generally prefer the constructive solid geometry and boundary representations, and hence they are widely used for generating complex structures. It is a question of trying to balance out whether you want to have very fast animation or very crystal clear pictures. You cannot have both. You can have both, definitely. You are hypothetically talking of very fast memory, very fast processor, multi-processor architectures, very large frame buffers handle and all that. Bandwidth crunch problems could be there in terms of loading the frame buffer in terms of memory. So, in terms of efficiency, do you want a very crystal clear picture with very little or small amount of animation, or do you want very fast animation, things moving very fast in the picture, typically in video games, then those characters and the solids may be approximated very coarsely. You may not have very complex representations of those structures. So, in terms of efficiency, both in terms of speed as well as handling complex structures, and let us say you want to provide high quality pictures, you can't have both speed and that. Okay. So, if you want to have speed, but you are satisfied with smaller quality objects, you better go for Octrees, because you can have hardware which are suited for this, but the pictures will be very coarse. They will not be sharp, and not much details in the objects will be available in the results, but you can make the pictures work very fast. Whereas, for algorithms based on constructive solid geometry and boundary representations, where you need complex pictures, but very little animation, you can use this to generate highly complex structures with lots of different complex solid objects put together. Okay. So, this is where we end up the lectures on solid modeling, where we will say it is mostly towards constructive solid geometry or BREPs, boundary representations, which are mostly used. So, although I talked about solid modeling, but mostly I did spend time on these two, the constructive solid geometry and the boundary representations, which are the most commonly used representations for solid modeling. We move on to the next lecture. We will see, based on these solids, at the last stage of the viewing pipeline, what do you need to do algorithmically to paint a particular polygon and give it a shade or a color. Thank you very much.